questions very clearly. Just gonna do that. Just let me know if my screen's visible to you. It should be there now. And so
Yes, it's
I
visible. Yeah.
okay. So and um, I'll let you ask me questions in between whenever it is. So feel free to stop me at any point. Okay.
Yeah, sure.
So
Please go
in
ahead.
eclipses,
Yeah.
as we said, we are observing the otherwise hidden. Okay. Um, I mean, eclipses are spectacular, cosmic events, which, as you mentioned, and definitely there is to this spectacularity, the idea that the whole event when it happens, it's a fast-paced event, and you see in a succession of moments lot of things happening, and the moon is the one which hides the bright layer of the sun, the photosphere, which we usually see in the sky, and as a result of that, hiding the bright layer of the sun, of solar eclipse of 2017, which was taken. So I'll just play that out again to sort of see how spectacular the event is. This is the wide view of it, where you can see the sun over there, and the moon. The disk of the moon is covering the sun, and you see the corona around it. And this is something towards totality when it is achieved, and then you see the corona as well in all its glory. So the reason you asked, as in, first of all, why eclipses happen. So as there are three things which are happening at this moment. So what is going on is, first thing we notice is that the moon is going around the earth. Okay, that is something which is that two nearby celestial bodies, the moon and the sun, which are involved in the eclipses. So the first thing is the moon is going around the earth. Okay, and it goes around the earth, and that's why we see different phases of the moon occur. the, it so happens that when the earth is going around the sun, it goes around in an orbit. This orbit, it lies in a plane, the plane of orbit of the earth, and then the earth is also rotating about itself, that is, which is causing day and night to happen, right? So the rotation of the earth, if you look at the diagram here, the rotation of the earth is happening around an axis. Okay, this particular axis of the rotation of the earth, and if you take the orbit of the earth, which is happening around this particular elliptical shape, there's an angle between them. Okay, the axis of the earth does not quite is not perpendicular, right, upright, but rather it is tilted. So there is a tilt to that. So the rotation is happening at a particular tilt to the orbital plane of the earth. So what therefore happens is, there are three things which are being combined. The two things here are, so one thing which you have is the earth, and way more bigger than the moon. But it is like this: imagine, let's say you are there in a on a in a very long corridor. Okay, and you see something. Let's say you have a there's a truck standing by, and then there's a car which is standing, but we know the size of the truck is much larger than the car. So if a truck is behind the car and the car is between you and the truck, it will not cover the entirety of the truck. But suppose the distances happen in such a way, because as things go farther and farther, as the truck goes farther and farther away from you, there will be a distance at which its size, its apparent size, how it looks to you, will match that of the car at a particular distance where the car is kept. So if the car is in between you and the truck, it will cover the truck in its entirety. And it so happens that the distance of the earth to the moon and distance of the earth to the sun is such that when the moon comes in between the earth and the sun, it is able to cover the sun in its entirety. Right? So these three things are sort of important. So what happens when these three things happen together, all of them? So this is the idea here once again. The Earth going around the sun and the moon going around the Earth. Okay. So what happens is, as the moon is going around the Earth, there is this 5-degree difference which is there. Okay. So due to this 5-degree difference, if the moon is too high, again, at this particular position, it is between the Earth and the Sun, but it's too high. So its shadow will not fall on the Earth. Or if it's too low, again, its shadow will not fall on the Earth. The same thing over here. The Earth is going around the Sun. It could be in this particular position, and the Moon is going around the Earth. It's too high or too low. But sometimes during this thing, what happens? The Moon, since it's going around, it will lie exactly along the central line, joining the sun and the earth. Okay, like for example, over here, these two places are called nodes. Okay, where the two meet, where the gray circle, which is the orbit of the moon, and the central line, they meet. So there it falls on the earth. Okay. And the same thing is happening on this particular side. It's diametrically opposite. The moon is over here, and the shadow of the moon is falling on the earth. During the same time, we know the motion of the moon is much faster. It takes, 29 days to go around compared to the motion of the earth around the sun. So a solar eclipse is almost always accompanied by a lunar eclipse, because just after the solar eclipse has happened, the moon will keep on moving, but the earth is moving very slowly. So the moon will reach on the other side, and then the earth would be in the middle of the sun and the moon. So the shadow of earth will fall on the moon, and so we have a lunar eclipse happening. So lunar eclipses and solar eclipses happen in pairs almost all the time. And so therefore these three things are something which are required in order for eclipse to happen. So this is what lunar eclipse is, when the Earth's shadow is falling on the moon, but the other way around, when uh, the moon is between the Earth and the sun, it is able to cover the entirety of the sun because of the angular distance and the distance between the Earth and the moon and the distance between the Earth and the sun, and therefore you see the eclipses happen. Okay, so that's why the eclipses happen, which is something which is needed. But then another thing, the question, why is it happening in Europe and why not here in India? This is again something which is seen over here because the Earth is rotating. As I said, it's rotating around itself, and that is why what causes day and night. So the shadow, when the Earth rotates, the shadow of the moon, it moves. Okay, so when it moves, it falls on certain areas of the earth, because only for that particular time, when the moon is in between the sun and the earth, the shadow will fall on the earth, and it will fall therefore only on the specific places which we call the path of totality, places where you can see the solar eclipse. The other places, like for instance, today's solar eclipse is happening around 8 p.m. in the European time, and during that time we will be in the darker zone because it will be midnight over here almost. Okay, so therefore we would be on the other side, and hence we will not see the solar eclipse. The eclipse would be seen where the sun is still there and the moon is there to hide it. Okay, so um, this is something, the solar eclipses have been happening for a long time. I mean, this is something which people since centuries back have been noticing. Even the ancient records found in India, China, as well as in Mesopotamia, they point towards that the eclipses happened. And as you saw, these are spectacular events. So the moment they would be happening, I'm sure people, whoever would be witnessing them, they would be keeping a record of them. So the records were there, but specific scientific records they sort of started around 1700s, because that is where the math and the physics sort of developed. So as people started not just viewing eclipses, but also predicting them, when they will happen, where they will happen. Okay, so this was Edmund Halley's map. So he made a prediction using Newton's laws of physics where the eclipse will happen, and it was happening in 1715 in UK. And so he made published a map of it, and then the eclipse was actually witnessed according to the map. So there was also, it's also provides a confirmation of your physical laws, because you use those laws to predict something, and then it happens then and there. So it gives you a prediction of that. So therefore the eclipses, people started making again written records of those. This is a drawing of the eclipse of 1715 at Cambridge, England. And then here's a map of eclipse from 1869. It also shows that people recorded that indeed during the eclipse they could see the solar corona. And not just the solar corona, there are also outer regions of the sun which are what are called prominences, where the gas in the sun, it's going spilling outward. Okay, so these olden records started, people started really understanding when they saw the solar corona. They started asking new questions. Hey, what is this thing made up of? What is really happening around the sun, inside the sun, and how is it also affecting events on earth? Let's say, for example, when you have the solar corona, there's a solar wind which is going around, which is emanating from the sun. And this solar wind consists of high energy particles, and they, when they encounter earth, that is what causes these northern lights, the auroras. Okay, so and these affect let's say communication on earth, because communication also depends on how we, when we communicate, the satellites and all that, the communication systems are they can get affected by the solar wind. So it's very important to understand the sun, and eclipses provide us a way to see the solar corona. Okay, so that's something which is there. Any questions on things till now?
We have a few solar eclipse, few people who have
Okay.
joined. Anyone has any questions for Dr. Surjit Singh? You can ask in between also. He is giving us time. I don't think so. They may be waiting for the end of the
Okay.
session. You
Okay.
can continue.
Okay. So that's also one thing you notice is that whenever we are studying celestial objects, we are studying the sun or any star or something like that. What is it that we are getting from them? Primary thing that we are getting from them is light, and that is something which is used to study those objects. Okay, and light comes in different wavelengths, all the way from radio to gamma rays. So there's a different spectrum of electromagnetic light waves which are there. So you have radio waves, you have a microwave, you have infrared, and this is a small region which is called the visible part of the spectrum. This is something which our eyes are sensitive to. So when we see something, we are actually sampling this part of the electromagnetic spectrum. This is the light which we see, but light comes in all different varieties. You have ultraviolet light, you have the X-rays, and then you have the gamma rays. And everything which, when it is sending out light, there's certain physical phenomena or something which would be happening, which would be sending light in different wavelengths. And in order to understand that thing, we need to really get light in all possible wavelengths, and that tells us what is happening, what physics is going on, what phenomena are happening in that particular thing. So here's, for example, a galaxy seen in different wavelengths. This is a whirlpool galaxy, and this is how it would look like if you would look through a telescope, because you are sensitive to the visible part. But if you had eyes of an infrared that could be sensitive to infrared radiation, like JWST telescope is, for example, or if you look out in radio, or you could look out in UV or X-ray, it would look very different. And but all these things are tied up together, because the phenomena is, all the physical phenomena is tied up, and in order to gauge what is happening, you need to see through all of them. This is something which we call multi-wavelength astronomy. And the sun also presents itself in different wavelengths. So if you look at the sun, for example, in all these different wavelengths which are there, this 4500 angstrom, this is how you would see with your own eyes, because this is something which lies in the visible range. But all these other wavelengths are not in the visible range. So therefore, in order to understand what is happening in the sun, you need to look at uh, different wavelengths, and you do what is called multi wavelength astronomy. But it does give you a way to see different regions of the sun. For example, you can see one of the surface, which is the photosphere of the sun. If you look at light in 304 angstrom, you are able to see the chromosphere of the sun. Then, if you go to a different wavelength, 171 angstrom, you are able to see the upper transition, the corona of the sun. But this is the quiet corona, and then you go even higher. I mean, let's say 193 angstroms. You see, there's a lot of activities which is going around in the sun, which otherwise looks very boring to you if you were to look at it with your own eyes, but with a safety glasses and safety filter put in, not with the naked eyes. Don't view the sun with the naked eye; it can blind you. We always, whenever we see the sun, we see it using certain safety filters. But when you look at it through safety filters, this is how it would look like, or this one. But this looks quite boring, as if nothing really is happening. But if you change your wavelength, you see it is quite active. Okay, and a lot of activity is going on. So, as I remarked, solar eclipses are an astrophysical laboratory. It allows you to study the sun, what is happening in the sun. It has also led to major discoveries. Okay, like for example, is the existence of helium. It was actually observed on August 18th, 1868. That's just 6 days from now, but back in the year 1868. This was detected by a French astronomer, Jules Janssen, during a total solar eclipse in Guntur, India. And what this guy did was he looked at during the solar eclipse, he looked at what are the wavelengths which are coming from the outer region of the sun, the corona of the sun. And he saw that there is a particular line, a particular yellow line which is coming, which is very close to two other yellow lines which come from sodium. If you take salt, common salt, which is sodium chloride, and you can do this experiment at home. I mean, you just need a flame, or if you have a gas stove, you just switch it on, it would burn blue. But the moment, let's say, you take some salt and sprinkle salt on it, you will see that the blue flame will turn to yellow. That yellow is actually coming from sodium. Okay, so every element has a characteristic light which it emits. So sodium emits this particular light. But then the Jules, what he saw was that near sodium there was another line, there was a yellow line which was much more intense than sodium, and this corresponded to an element which was not yet observed on the earth. Okay? There was a new line, it was not seen on earth. And he said that this probably this element is something which is there in the sun, and he called it helium. Helium comes from the word helios, which means the sky in Greek. Okay, and later on, when helium was actually found also on earth, and its spectra was noted, that light coming from that was noted down, and it was seen that this indeed matched the what the was observed on the sun. So it was first discovered on the sun, and then it was discovered on the earth. So that's discovery during the solar eclipse. And as I remarked, that there are various physical phenomena which is happening. So there's an interesting one which is telling you what is the atmosphere of the sun, how it looks like, because that is what we are seeing during the solar eclipse. So you see that is an interesting thing which is happening here. It's telling you, as I am going away from the photosphere. The photosphere, which we saw earlier, is the surface of the sun, which is visible to us when we look through the solar filters. Okay, and that's the bright photosphere, which is the bright layer of the sun, and that is the one which usually hides the all the atmosphere. The atmosphere is something which we cannot see because this is quite blinding. It's very bright, much brighter than the atmosphere. Again, this is something which will come to in the next slide. I'll show you that. But as you you go away from the photosphere, that is, you go higher and higher above the surface of the sun, called the photosphere. So you see the first layer which comes is chromosphere, and then there is a transition region, and then it comes what is called the corona. What this is telling you is that if you look at on this side, what is plotted is the temperature. The temperature of the chromosphere over here is around you know uh, between 1000 and 10,000 Kelvin. Okay, but as you transition from this is 1,000 kilometers above the sun's surface, the photosphere, you just transition from this 1,000 kilometers to just a few thousand more kilometers. Suddenly the temperature increases so much that it goes from 10,000 to a million degrees Kelvin. Okay, so the temperature increases sharply. This sharp increase in temperature is something which is very uncommon. I mean, if you look at the atmosphere of the Earth, we know the surface temperature of the Earth is around 30 degrees, right? I mean, this is some a typical temperature. Of course, you some places will have 50 degrees, some places it would be like 44 or something like or during the winters it can be less than a zero. But nevertheless, the typical temperature we'll say is about at the sea level is about 30 degrees. And but you know very well, as you let's say go higher and higher in the atmosphere, for every 165 meter that you go up, you there is a decrease of 1 degrees. Okay, so therefore as you go higher and higher, you are effectively going into cooler and cooler temperatures. Okay, so but this decrease which is there is gradual. It's not like an immediate decrease, like from 30 you would go to a minus 10 in a matter of let's say a kilometer or a 100 meter or something. But here it's in a matter of just a few thousand kilometers, there's a sharp increase from 10,000 to a million degrees Celsius. Okay, so which is something also called the coronal heating problem. It's an open problem again. Why the corona of the sun is so hot, a million degrees, and another question being why does it transition such sharply? Why is this sharp thing happens? Now, if you want to understand this particular thing, we need to really understand what is going on in the sun, and we need to observe it. Okay, and if you want to observe the corona, usually during your normal days, you are not able to see the corona. The reason for that is the brightness of the disk of the sun. So if the brightness of the disk of the sun is over here, this is showing you the disk of the sun, how bright that is. As you move away from the disk of the sun, its brightness of the atmosphere also decreases sharply. Okay, so the corona is way less bright, almost 8 orders of magnitude fainter than the disk of the sun. So, if during your usual days you are not able to see the corona at all because your sky is also bright. Sky is brightened by the sun itself. Because why is the sky the daytime sky is bright? Because of scattering. The sunlight enters our atmosphere, scatters around, and therefore the sky is bright. And the brightness of the sun of the corona is much below the sky's brightness. So therefore we are not able to see the corona at all. The sky and the disk simply dominate over the corona. But during totality, during totality, what happens during the eclipse, the disk of the moon comes in between. When it comes in between, it hides the disk of the sun. It hides the disk of the sun, and therefore also simultaneously, because the light from the sun is not coming out, it's not scattered that much by the sky. The sky at eclipse, the brightness of the sky also drops down to this particular level. So therefore, you see, since this is the level of the brightness of the sky, the corona is becomes visible. The corona is becomes dominant, and therefore you are able to see the corona during totality of an eclipse. Okay, so that's something which is there. And the other thing which you notice is that the corona is made up of three parts. It's not just one. We call one is the K corona, there is the F corona, and then there is the E corona. Okay, so the difference between them is just a matter of the E-corona is something which is due to coronal ions. The difference is how what is the origin of these three different parts. So E-corona is the emission corona by the elements, what we saw earlier, which the the French astronomer observed. So he observed this. Then there is the F corona, which is caused by the interplanetary dust. And then there is K corona, which is caused by the electrons around the in the atmosphere of the sun. Okay. So, and you see as well, as you go outward from the sun, brightness of the corona is also decreasing. It's not that it is equally bright, but its brightness is decreasing, and it decreases also, it decreases several orders. So it's near the surface of the sun. It is around 10 to the power minus 7 in terms of the disk, and then it drops by two orders. So brightness of the corona also decreases. So it's something which we call as a very high dynamic range that it presents radially outwards around as you go outwards out from the disk of the sun. I mean, this is something which you see over here. So this is the disk of the sun during totality. So the moon is covering the sun, so you cannot see the disk of the sun, and therefore, as a result of it, the corona becomes visible. The corona near the limb of the sun is much brighter, and as you go away from the limb of the sun, radially outward, you see that the corona is becoming fainter and fainter. And this is what is happening here as well. As you go away, it becomes fainter and fainter. All the three components, they become fainter and fainter. What you see here are is the component which is K plus F. These two components combined are giving you the corona here. The E component, as I said, is emission lines. Those are what are seen when you use a spectrograph and you see those lines which we saw earlier. I'll come to that. How do you see the E corona? But this is K and F corona combined, and you do see that its brightness is going down as you go away from the sun. Well, nowadays we are also doing solar astronomy, and we are studying the sun from space. We have our own Indian mission, which is Aditya L1, that is doing the study of the corona from space. And then there is another one. It's a very interesting experiment that is happening from the space. Is what is called Proba 3. It's a European mission. What it basically has is there are two spacecrafts or the instruments, and they are moving about the earth. They are orbiting the earth. They're such that their setup is such that one spacecraft comes in front of the other. So usually we cannot have the eclipses do not happen. Eclipses require that you need to block the sun. Okay, so you need something to block the sun. So how do you block the sun? So these guys, what they did, they devised a way by which you have two different spacecrafts. So you have the one of them. If one of them comes in between the sun and this one, then it can make an artificial eclipse. So this then blocks the sun. This looks at the sun behind it, and then we are able to have an achieve an artificial eclipse, and then also study the sun. Okay, so but then the question is, when we are doing all these things from space, what is it that is there for doing science with ground based eclipse experiments? Okay, why is it necessary still to do go to eclipses where eclipses are happening and then do science and run some experiments there? Well, the idea here is that there are different reasons to actually do still study eclipses, even though the natural eclipses, even though we are able to make artificial eclipses now. The reason is that um, you see, when you make these spacecrafts or satellites, they're always made for a certain specific purpose. There would be a certain mission which would be related to it. There would be a certain science objective. Okay. And these particular science objectives, they're always, you have to, the missions are planned. So these configurations are logged in many years advance in of their use. Okay. So let's say you found a particular science goal now, but because your spacecraft has always already been logged in for a certain different science goal, you cannot do that particular, you cannot test your idea at the moment. You have to wait and then build another spacecraft which would have that particular goal, and then make an artificial eclipse that you do it. So therefore, doing the study of eclipse, I mean, doing science where natural solar eclipses still matters. And then there is another reason is that the low corona, uh, it can be I mean, it can be monitored to some extent from mountain-top coronagraphs. You can build these coronagraphs, which are telescope, which have an occulter in, at the objective end. But then this occulter, it hides the lowest corona. So, and its images are noisy and show very less detail. So eclipses, in an eclipse, nature has given us a natural occulter, the moon. So it hides it, and we are able to therefore study the corona all the way from near the limb of the sun to very far away into space. Okay, so and also, the Eclipse expeditions have flexibility. You are able to use the latest equipment and take advantage of new theoretical ideas to frame your observations. And they give you a variety that you can use different, telescopes than larger telescopes than space, because you cannot really put heavy payloads. The what you can put in space are sort of limited by whatever rockets you have. So, but on the ground you can use whatever how you can go as large as whatever you want. So you can design different experiments. It's also less expensive than any space instrument. So even after allowing for weather failures or something, so you can have a variety of information that can be obtained. And then finally, let's say you want to do something in space, you may want to test it first. So therefore, the eclipse ground based eclipse experiments also offer what is a test bed, so way to test equipments and methods that would be destined for a space launch. Okay, so so there are different science that we do with eclipses. You We are able to merge eclipse and space observations. So here's, for example, a case where you have an observation from space, that is the outer region, and this is the inner region, is the observation from during an eclipse. So you're able to merge them. We are able to test general relativity at eclipses. In fact, this is how in 1919, when Eddington did the experiment, Einstein predicted that light would be bent by the sun twice than that prediction predicted by Newton. And Eddington went and did the experiment in 1919 and found indeed, yes, light is bent twice than what was predicted by Newtonian gravity. And that's how general relativity came into was verified observationally and made Einstein a celebrity. But when Eddington did it, he did it in 1919. The technology was way more different than what it is now. So we can still do test general relativity which with even more precision, and that is what people are also trying to do. Here's a paper which mentioned a century of light bending measurements, and then there is a modern Eddington experiment. You did it with modern equipment in 2024, and we are also trying to do this particular thing in 2020. In today's eclipse, people are this is sort of a practice based thing because of certain science goals, but uh, we are destined to do this particular experiment in 2027. You are able to detect fine scale coronal dynamics. You can predict the solar corona using the models of the sun. You build a model, what is happening there, what is the physics happening, then you predict what would be the shape of the corona, and then you actually see it during the eclipse. So that verifies your physics. Okay. And again, as I mentioned, the heating of the solar corona is something people have been studying. This is the E corona, how it looks like. I showed you what K and F corona together look like. This is the E corona, the ambition corona, which gives you different lines over here. And then the sun has strong magnetic fields, just like the earth has magnetic fields. The sun also has magnetic field. And how do you study the magnetic field of the sun? Again, you look at the coronal lines. You trace the solar corona, and that tells you, because it's a magnetic field underneath that is driving how these corona looks like. So if you look at the corona, you can then find what is underneath magnetic field that is driving it. So you can find the magnetic field and the of the around the sun and the atmosphere of the sun. Okay, and that is what is also measured by something, as I mentioned. What we get from the observations is light. There is a particular property of light which is called polarization, and this property of light, which is polarization, is the one which allows us to actually study the magnetic field. Okay, this is the experiment which we also did in 2024 to actually find the to observe the polarization of the solar corona. I'll come to that, and hence therefore try to map what is the magnetic field structure around the sun in the atmosphere of the sun. Okay, so there have been, as I mentioned, uh, a lot of technological advancements, and they allow us to do these experiments way better than what had been going on in the past. Like the 1919 experiment of Eddington is there's things are way different now. We have state of the art imaging equipment. The cameras are state of the art, which are there. We have portable equipment available. If you should go back and check what is the equipment which Eddington used. That telescope was huge, but it was not huge in the sense that it would was meant to do it, but the technology was the way it was, and he used photographic plate to actually get the the where the stars were, and then see how the light is bent because this position of the star shifts due to bending of light. But nowadays we have portable equipment which is available, state of the art. We also have computational power which is available to apply powerful techniques. When we get images, we get the data. How do we really process them? We need to work on them. We have a lot of processing power, computational power, in order to work on the data. So that allows the doing all these experiments with cutting edge technology. Okay. So, how do you do that? This is something which I also put an article very recently. It's an experimental guide for total solar eclipses. If anyone wants, they can certainly, definitely, I'll recommend going and checking the article out. It's there on archive. For people who are not from scientific background, let me sort of just explain. Archive is a website where all us we scientific folk, we put our papers there, which are called preprints, before we send them to a journal for publishing. Because when the paper or any article goes to a particular journal, it goes there, it goes through a peer review process, and then it gets published. So archive is a place where it's open access to all the papers which are there, because journals usually don't have open access because you have to, they're behind paywalls. But nevertheless, there's just a small digression there. But archive is that particular it's a where all everyone every morning you see a bunch of new papers which come up. All the research is something which is put on archive, but of course it goes through certain moderation. So all every it's a proper scientific archive, the repository which is there. So there's something which is there, and let me just sort of mention a few parts of what you need to do when if you want to go observe an eclipse or do a certain experiment. What are things which you should be sort of aware of? Okay, and this is something which everyone should do at least once in their lifetime, because it's such an event which is there. Okay, so first thing, as I said, I mean, it's not happening everywhere, right? I mean, we saw why does it happen everywhere. So there's certain places on the earth where the moon shadow falls and it travels during the rotation of the earth. So you need to therefore put yourself in the path of totality. Okay, so here's, for example, all the paths of totality of solar eclipses from 2021 to 2041, and you see there are different eclipses which happen. The yellow ones are the ones which are total solar eclipses, where the disk of the moon almost completely covers the disk of the sun. The coverage is more than 99%. Then you have the orange ones are what are called annular eclipses, where the moon is slightly closer, such that it does not quite cover the entire disk of the sun. But what you rather see, the moon is slightly closer, so you see the moon of the disk of the moon, and but there is an annular ring around it, so the sun is still visible. So since there's an annular ring around it, and that is the bright photosphere, you are not able to see the solar corona because you're not quite covering it up. And you have to be very safe in viewing an annular eclipse. That requires your safety glasses to be on for the entire period. Whereas for a total solar eclipse, I'll come to a point where you there is when you have totality, you can actually take off your glasses for only a moment during totality because the disk of the sun is covered in entirety. Then you have hybrid eclipses, which sort of start as annular and then they become total as they go because the distance between the earth and the moon is changing. So you see some of the eclipses over here. The one which is happening just now, that is the line 2026. It's over here. So it's happening in
and then
Iceland,
they
Greenland,
become
and parts of Spain. Um, the next one will be in 2027, August 2nd. Again, that will cover this particular line over here. This is the path of totality. Majority of North Africa, Morocco, Egypt, parts of Saudi Arabia, the Horn of Africa, that would be covered, and then it'll go over to the ocean. And then you have the other eclipses coming. There'll be 2028. It'll be the path would be on Australia, and then there's an interesting one from our side in 2034. The path will go. Uh, it will start from over here, Atlantic, from Africa over to Arabia, Saudi Arabia, and enters the Indian subcontinent, and you will be able to witness totality in Ladakh. Okay, so that's something which will happen in India at that particular point. The annular eclipses, of course, will also happen in 2031. You can see it from the south. So, if you want to observe an eclipse or do a certain science, uh, of of course, the first thing which you should definitely do is observe it. But if you want to do science, it's an amalgamation of physics, math, and engineering. You need just work out physics about it. There is math which is involved because you're predicting eclipses, finding things out, and all that. And then there's engineering because you need to use all this equipment to actually do plan your observations and do your experiments. So there's a whole lot of equipment which is necessary. This is the equipment something which we used during our experiment to record the polarization of the solar corona in the visible band during 3 minutes of totality in United States in 2024. So there's a lot of equipment which goes in. I'll come back to this again once again, but this is just to show the some of the pictures from the eclipse. Is again our equipment there, observations in one camera which is there, the three of us who were there doing this particular experiment. So what happens during the eclipse? This is what the thing is. Well, the sun is moving across the sky from east to west. The moon moves slower than the sun and appears to move across the sun west to east. So the motion of the moon is on this particular side, motion of the sun is over this side. So of course they will intersect in between. Okay, and that is where the totality happens. So they have different contact regions. So the moon is going this side, over this particular side. The sun is moving to this side. So sun is moving behind it. So you see, there's a first contact which is C1 when the moon first begins to cover the sun. This is over here. You need safety glasses to view the sun because the sun is visible. The sun is 50% covered over here. This is partial eclipse. Again, because the disk of the sun is not quite hidden, you need safety glasses. The adrenaline pumping, time, it happens here at C2 when the second contact happens from C1 to C2. So C1 is when the first contact is happening. C2 is when the whole thing has moved over this side, and the second contact happens. The second side of it touches the other one, and the sun is first completely covered at the start of the total solar eclipse, and then it moves. This is the totality in between. So here in between, you can take off your safety glasses and view the totality with your naked eyes, and it's spectacular, literally. Okay. um And this happens for a very short period. It depends on different eclipses. For example, in 2023, the solar eclipse happened in Australia in Exmouth. The duration of the totality was 51 seconds, so it's fast. Um, in 2024, the duration was near. If you were near the path of totality, it was around 3 minutes or 3 minutes 51 seconds. So it's quite fast. I mean, it seems that as if, oh, you have 3 minutes, but uh, the moment this is happening, the adrenaline pumps up and you completely lose track of time. Okay, so it's so such an exciting event. So it is a very small event, a very fast paced event compared to various other events. So that's why I called it the fleeting laboratory. So this then you have the C3. The sun is about to be uncovered. That's the end of the total eclipse, and you need to put your safety glasses once again. And during this time, the telescope also needs to be so here you can uncover it, but are outside of C2 and C3, you need to also cover your telescope, because just like our eyes, the camera is also quite sensitive. So if the camera will be uncovered with a safety filter during partial phases, that is outside before C2 and after C3, then there's a chance of getting it destroyed, and you don't want that to happen. So you cover the camera with safety filters before C2. The moment C2 happens, you take off that filter, and then you can take images. And once C3 is about to happen, you put on your filter again, and then you carry on forward. Okay, so this is what is happening there. And at C2 and C3, there are certain effects which happen because uh, the disk of the moon is just about to be pulled away from the disk of the sun, and that gives you these things called Bailey beads and the diamond ring effect. So what you see is essentially this. So the whole sequence of events is something which is shown here. So you see this is where the C2 is just about to happen, that is the second contact is going to happen, and you see the bright photosphere of the sun is just about visible. So you are able to see this is what the Bailey beads are, and this is also called this is called the diamond rings. And then you see, due to the irregular features of the lunar limb, you see these Bailey beads over here, and then you see totality. And again, after totality, the disk starts to go away, and then you see the Bailey beads once again, and then you see these are the beads over here, and then you finally see the diamond ring, and then the partial phases begin once again. So that's the fleeting moment during which this happens. And you can see the solar corona during the totality. This is again another images, a few images of our team, me and students of mine. We went to for the total solar eclipse in 2023 in Australia. We had our equipment at that particular time as well. So something just to notice. Um, we are involved. So as I am an astrophysicist and I do various things. I work on quantum gravity. I work on cosmology, early universe, black holes. Also work on galaxies. Solar corona is also something which I work on. So it's different, a wide variety of my work areas, and we are involved in solar corona research at IIT Delhi. We are building up, as I mentioned, they're different. From we take our data and then we have to also work on the data. That is where the computational power gets utilized. So we have built different pipelines to how to work with the solar eclipse images over here, and that's how you get to know what is happening. So you see the solar corona which is over here, and as I said, it's mentioned before, it's readily outward. If you look, it's the brightness is decreasing. If I just open this thing up, I cut it over here and open it up, you see these streamers. So the corona is not uniform, but it has these streams. Now, what is the cause of these streams? It's the magnetic field of the sun. There is a magnetic field of the sun that is being traced out by the corona, the light which is coming from the electrons around the in the atmosphere of the sun. Okay, and to this is what I mentioned is two different components. So here the components are K and F combined together. Okay. So we wanted to achieve, we wanted to look at, hey, how do we find the magnetic field of the sun? So in order to do that, I mentioned that this property of light, which is coming from here, if we are able to find out the polarization of light, what is the degree of linear polarization, that maps directly tells us what is the number of electrons around it, and number of electrons is related to the magnetic field. So that is something which we wanted to find out. So this is how you start. You pose it, you pose a certain question, then you see what is it that you want to observe, and if you want to observe it, you need to do engineering. So this is what the engineering which we did. We designed our own filter wheel, set up a certain way how to actually find the polarization, how to measure the polarization, and we had this particular equipment, and we placed ourselves in the path of totality. So this was the path of totality in 2024, and this is where we were at Dallas. Okay. And when this thing is happening, there are a lot of things you have to worry about. There's also the weather that you are sort of fighting against, because often at times there could be overcast, there could be raining, and then you won't be able to do the experiment. So you have to but it's not really a failure, but something definitely needs to be done. So, like for instance, I'll just recount uh, my own experience over here. Originally, we had planned to place ourselves here, which is a place called San Antonio, also in Texas, United States. The reason why I chose that, because we looked at for what was the pattern of weather in last 20 years. That is, in last 20 years, where were the places which were overcast with clouds, and which were the places which were clear. And what we saw in the 20 years was that places all over here were clear in the last 20 years before 2024, and places all over here were clear. Sorry, yeah, so these were clear, and all over here was overcast on the day of the eclipse. So this happened on April 8th. So on all April 8th, back 20 years back from 2024, on those on all those days, this particular region was, most of the time, 77% of the time, it was overcast, and this region was clear. So that's why we chose to stay here. Okay, by that particular insight, that 77% chance this would be overcast, and this most of the time 80% chance this would be clear. But it so happened it became a reverse on in 2024. This whole region was overcast, and this whole region was clear. Okay. But plans were already made to be here. We had to, at a very last moment, think what to do. Of course, you cannot. If you're in the United States, you cannot go off to Canada in a blink of an eye, right? And of course, and going all there, it requires a lot of planning. I mean, all sorts of formalities need to be taken care of. You have to take your equipment and all those things. So we therefore decided that for the 3 days prior to the event, I mean, it was all about, we were glued to the TV and to the weather reports, seeing, hey, what's going to happen? What's going to happen? So we found that if you go north, it there is a chance of things becoming clearer. So therefore, we shifted our base from San Antonio to Dallas. And fortunately for us, um, this is again what happened. The day of the eclipse, 7:30 a.m. The eclipse was at around 1:44 p.m. At 7:30 a.m. it was overcast completely. Okay, and but I still said, okay, we will still set up our equipment. It will still go ahead with we'll wait and see what will happen at 1:44. And lo and behold, uh, it cleared up during totality, and that's how we were able to do our experiment and get our data. Okay, so the totality spanned 3 minutes 52 seconds, from around 1:40 p.m. till 1:44 p.m. 35 seconds. So the central daylight, central time, and this was our location, the latitudes and longitudes. We noted them down, and this is the equipment that we used. And so we had as I mentioned, you need to keep your telescopes also covered during the partial phases. So you need these solar filters. You take them off during totality, and then you put them on after C3. So you have a bunch of equipment which is there. You need to also during the sun, you have your laptop connected. This is how you are noting everything down, the imaging, watching everything. So we put up a suitcase to in order to shield it from the bright light of the sun, so that we are able to see the screen. And there's a bunch of different equipment which is required. Again, to those who are really interested, they can go and check my article, and a lot of things, everything is sort of mentioned over there. And we when we got the data, we also worked on it. This is a separate article, not yet out yet. It's been sent for publication, and soon when it will be out, I'll also be uploading it on archive. So we organized, we designed our own ways to how to work with those images. This is a snapshot on how we aligned our images and added them together. And here's something which one of those results which I really want to point out. We wanted to look at the polarization. Okay, so think of it this way. Earlier, when I showed you the corona of the sun, it was all white around it, right? So that was just telling you how what is the brightness, and we saw that the brightness decreased as you go went as we went outward. Now, if you I told you that there's a certain property of light which is called polarization, and if I want to see brightness as well as the polarization of light, what I did is what we did, and some people do is that you color code the polarization information. That is, color is telling you the brightness is telling you what is the amount of light. The color is telling you what is the degree of polarization. So that this brings out a new way to really, picture the whole thing. That you are picturing simultaneously the intensity of light as well as this property called the polarization of light. And by giving polarization a color, so this is not really the real color, but rather the degree of polarization has been given a certain color. So it's a false color. Okay, and so it gives a way to visualize what is how the polarization angle is changing, and gives a very, a chromatic treatment, a rainbow kind of an appearance to the solar corona. And this different polarization is actually mapping out the distribution of how the electrons are distributed in the atmosphere of the sun, and hence also how the magnetic field is distributed in the atmosphere of the sun. This is actually mapping out the magnetic field. Now you can do a certain more processing on it in order to see those, trace those magnetic lines. And when you do that processing, this is what it looks like. Okay, so you have these streamers which are going out, and these streamers are what are tracing those magnetic field lines. Okay, you can see the moon over the disk of the moon over here, and which is covering the central disk of the sun. And the color, as I said, is false color. It is encoding the polarization, the degree of linear polarization of light coming from the outer atmosphere of the sun in the corona. And of course, you see, it's not just the polarization. As you go outward, the intensity of the light, the brightness is decreasing. That is something which is there. So this is something which we did. And when you do go look at it, do an experiment, you do a certain explore a certain aspect, and this is something which, as I mentioned, this is something in the calculations and stuff, which the science which we did. It's there with the article is still it's under review. It will be published soon, and we are also analyzing the magnetic field around with this particular data. We're doing that particular science, but what when you are done, when you have observed an eclipse, let's say you've gone there, you've seen the eclipse. Once the eclipse gets over, you start talking about the next one. Okay, and the excitement builds up. You count down to the next eclipse. The countdown happens in months, because let's today is the eclipse which is happening in Europe in 2026. The next one is 2027, and you start counting back in months, then days, finally hours, and then minutes, and finally seconds. That is what an eclipse is all about. So I hope some of the questions which everyone has about eclipses, why they happen, where they happen, and what we can learn about these eclipses, how to observe these eclipses, and what science we can do with these eclipses. I hope I have been able to answer many of those questions, and I'll take if any more questions which you may have um, at the moment. Okay. Yeah.
Thank you so much, Dr. Surjit, for giving us such an insightful details about the solar eclipse. I was fascinated with the images that you have shown because that are, of course, not visible to everyone, even if we are watching a solar eclipse with taking all
Yes.
the equipments and all. So, any questions for Dr. Singh?
Um, Sir, there is one question from the YouTube chat.
Okay.
I think you have answered this, but I'm still mentioning it to you.
Sure.
So, Braj Kishore Sharma is asking, is there any possibility of a satellite consisting of a big disk which is big enough that blocks the sun in the same way and giving us more time to study the corona from
Yeah.
Earth only?
Indeed, indeed, it is the something which is there, and that is what the program mission was. And in fact, it has started giving us the data. This is something which has already happened. But I just want to point out once again that you are keeping two satellites. One is the occulter, the other one is the one which is viewing, and you are keeping them. The distance which was kept between them is 150 meters. This keeping this distance, because you have to do it to observe, make an artificial eclipse, it requires an immense amount of precision in space. It's not a easy feat. And Proba 3 was is actually the first mission to do this particular thing, to keep it has two satellites in a fixed configuration around 150-meter apart. It was a technology demonstrator as well, and we plan to have more such. Once we've seen that, yeah, this is something which can be done, we are planning to have more such missions with new science goals to look at.
All right, so thank you so much. This was it. Yeah. Over to you, Nia, ma'am. Okay, so there's one more question.
Hmm.
To drop in the chat. The question is, like, how is it different from the Parker space probe, Parker solar probe? Like,
Okay.
aren't that,
The
yeah.
Yeah, the Parker Solar Probe is uh, uh, not doing an eclipse
So,
observation, but
it does.
rather, yeah, Parker probe is something which was sent out, which actually goes near the sun and does in situ measurements there. That is, it takes images of the sun close to the sun, okay, and is also doing measurements of the solar wind near the sun. So that is what this Parker solar probe is. It's actually very similar to what our Aditya L1 mission is. Aditya
Right.
L1 mission is something which was sent out. It is there at what is called, the name is L1. That tells you that it is at what is called the Lagrange point 1, and it is over there, and at that particular location, it has various payloads, various different systems which are there. One of the payload is coronagraph, which actually has a slit, and that goes around and samples the corona and looks at, is basically something which is looking at the e corona. And then there are other instruments on Aditya L1 which are also doing measurements near that point. There is one which is also, there's a magnetometer there which is actually also measuring the solar wind activity, but at point L1. Parker Solar Probe can go much closer to the sun. Yeah.
All right, sir. Thank you so much.
Yeah.
Over to you,
Thank you
ma'am.
so much. Yeah, thank you so much, Dr. Surjeet. One thing, if you can share with us the most memorable solar eclipse till date that you have seen and why.
Yeah, well, the 2024 eclipse was a longer one, and we did this experiment there. It was something I hadn't before this. I hadn't done any. Well, we took our equipment in 2023 as well, and that was where, this is the thing which I mentioned. Um you uh, you plan something, carry it out, so it becomes like a practice session for you, and then you execute it. So it's not just really a one phase activity. So it's a whole planning which goes on. And so for me, 2024 and 2023, but actually, in fact, both of them were really special because we could plan this particular experiment, the polarization experiment, and also, of course, I was a team of students with me, so I could, share the those moments with students. Some, because the previous eclipse which I have been, I was did not have any students at that time with me. That was something which I was doing a solo. So doing them with students, sharing that thing, it was a really good thing. It was really exciting, made them special. And we are planning. There's also we this an Indian science community, the solar physics community is sort of being brought together, and we are planning the next decade of solar eclipse experiments. There's going to be a meeting on it in December this year.
Okay, looking forward to that. One more thing, you were talking about like students and all are around you, then it makes a difference in analyzing and observing things. Can amateur astronomers collect some eclipse observations that are genuinely useful to professional scientists like you? And if yes, what kind of observations or measurements would you recommend?
For amateur astronomers, you mean?
Yeah, yeah.
Oh yes. So quite a bit. In fact, so if you want to do design certain experiments like the looking at the corona, the polarization or something, they require a certain bit of assembling a special equipment to do that and all that. But as I mentioned here, there are different experiments which can be done. So here's one of them, which is there, the modern Eddington experiment. Although this also requires a bit of planning and execution, but this is more of where you are just doing not with much equipment, but you just have a camera and telescope, and then you are doing certain observations. And if you have, and this requires the working with this thing, this experiment requires that there could be many stations. So if you, let's say, have stations at different places along the path of totality, there might be certain stations which may have bad weather, but there could be other stations where there could be good weather there. So amateur astronomers can definitely go and do this particular experiment, try to see, carry out this, get data for this experiment, and whatever data they will provide will certainly be useful in one way or the other, to conduct to do the study of bending of light. Okay.
Okay, and since we already have so many sophisticated satellites observing the sun continuously, uh, what are these few minutes of total solar eclipse still scientifically so much valuable? How do you suggest these amateur astronomers that these are the moments that they must and they should try to capture from different parts of the world as much as possible for them?
Yeah. Okay. So for amateur astronomers, there's another thing which I would really like to emphasize. When we have these space telescopes and working, often we are professional astronomers are have an access to them, and we are able to work with the data, do science with it. But science is a study which is an experience. I mean, in the sense that it's an experience that should be gathered, that should be had by everyone. Okay, and let's say, for example, and each one of us, even not just in the case of an eclipse, but in case of an amateur astronomy, there are always these questions that we often encounter when we learn science, when we do in our schools and various other places and all that. uh, we often hear facts, right? We sort of learn them as facts. Hey, well, the earth is going around the sun, the moon is going around this earth, and it's going around in an elliptical orbit. Certainly, amateur astronomers can go use their equipment to actually verify those facts. Okay, and experience those facts. It is when you really experience those facts, you actually have gone out and actually worked. I mean, if people 300 years back could do it, certainly with the equipment which the amateur astronomers possess at the current time, they can definitely do that. Okay, and so you're not taking facts at face value, but rather are experiencing it. So if anyone, being a person of science, if anyone else asks you, hey, how do you know that this thing happens? You have thing to prove it in front. You have an experience to show, and that is where something is important. And this is something which goes on for eclipses as well, even in times of the space-based missions. For eclipses, also for studying the sun, the ground-based eclipse research still matters individually, personally, as well as for even for such professional studies. So it's still it matters a lot. Yeah.
Yeah. One last thing. Since we are talking about these amateur observations, we will have thousands of them.
Yeah.
So, can ever they be combined into a scientifically useful data set?
Definitely. I mean, I can tell you one simple thing which can be done. Just have a telescope and a camera and just observe the corona. So let me just so let's say here's the path of totality. Okay, so on 2034, and there'll be a certain path which will be going through India, right? So let's say, or take any other path. If we station a lot of amateur astronomers at various points here, okay, and eclipse will happen at different times for each one of them. So you're getting the data for every one of them. So if you take that data, of course, it will be a very huge amount of data which will be there, but nevertheless, it will show you during these 4 minutes of totality at every point when the data has been observed, how does the corona itself change in time? This is the corona which we see over here. Uh, we see that it is, is something which is one instance of it taken from one station. Let's say you have different stations observing. So if we are able to see, will be able to see how the structures themselves are changing, because it is dynamic. It could be dynamic on a very slow scale, but nevertheless, this is something which can be, again, something which can be checked. This experiment was done also with the polarization in 2024 by Citizen Kate experiment, which basically what they did, as the name suggests, it was Citizen Kate experiment. Citizen science experiment means that lots of people in United States, they were a scientific team organized this particular experiment to bring out amateurs. They had them stationed across different the path of totality, get the data, but for polarization, and to see how the changes are happening. They're still working on that data because it's a huge data which was there, and the results will definitely be very useful and will give new insights. So there's something like that can definitely be carried out.
Okay. Anyone else has any questions for Dr. Singh? Oh, I don't think so, but you have answered almost all their questions, I believe, in your presentation itself. It was self explanatory, and it was such a fascinating journey into the science of solar eclipses. So, thank you so much for taking us
You're
behind
welcome.
the scenes and what is actually means to chase an eclipse for scientific research. You have explained all this in detail. A big thank you to everyone who joined us today and participated. I hope the next time you see an eclipse, you won't just look up at the sky. You will also understand a little more about what is happening, what to look for, and why it matters. At Astrophile Education, that's exactly what we hope to do: turn curiosity about the science into a deeper understanding of science. Thank you, everyone. Keep looking up, keep asking questions, and keep exploring the universe with us. Thank you, Dr. Sujit, once again.
Thanks a lot.